Hello, and welcome to this topic webinar tutorial on processing a PX dataset with CrysAlisᴾṕ, mainly directed at those of you who are new to the software. I am your host, Mark DelCampo. I'm a senior application scientist here at Rigaku Americas Corporation. I'm joined by my co-host, Dr. Joseph Ferrara, CSO of Rigaku Americas Corporation, and the Deputy Director of the X-ray Research Lab at Rigaku Corporation. First, I'd like to go through some housekeeping items. This webinar is being recorded and will be made available online afterwards, so don't worry if you miss anything. Second, the data set that we cover today will also be made available. Third, you can submit a question at any time by using the Q&A button that you usually find at the bottom of the Zoom interface. I plan to answer all questions at the end of the presentation. Finally, we invite all of our customers to join us at the Rigaku X-ray Forum. Today, we will work with the dataset that I collected on a CrysAlisᴾṕ Synergy custom instrument. This system had a Micromax 007HF rotating anode generator with a copper target. We used Verimax VHF optics, an ultra-fast UG2 kappa goniometer, and all diffraction data were recorded on a Rigaku HiPix 6000 HE hybrid photon counting detector. Here is a picture of the lysozyme crystal that was collected. It is a really nice 200 micron crystal. It's a tetragonal crystal, and from the diffraction data, we can see that it diffracts to at least 1.6 angstroms. I collected a data collection with a strategy to 1.7 angstroms. The data were collected with 686 images total over 3 different scans. And I would just point you to the fact that the total exposure time for this data collection was just over 2 minutes. If you're interested, this data set easily solves by sulfur SAD phasing, although we're not going to cover that during this webinar. So now let's get on to the data and the tutorial. So let me just give you a word about how we're going to organize the webinar. On the left-hand side of the screen, you're going to see the topics that we're going to cover on the top, followed by step-by-step instructions of what we're going to do. So the first thing we need to do is open the data set. We need to find our PAR file in our directory tree and double-click it to open. So everything else I'm going to do here is on the right. You can see that I have my data directory. It's titled LY with the date of January 24th, 2019. And so I'm going to scroll down in this directory till I find my .par file. Here it is. Double click it. CrysAlisᴾጴ opens in this experiment. Now I'm just going to quickly resize it so you can still see the topics on the left and the instructions. And we'll work with CrysAlisᴾጴ here on the right. So the first thing you want to do once you have your data set open is if you're working on a PX data set, you'd like to be sure that the software is in the PX mode. So you can check that very easily by looking at the bottom right-hand side of the interface. Look at the name of the software. It should say CrysAlisᴾጴ and have the letters PX. If it does not, if it has SM, you're in the small molecule mode. You just click on the program's name and you get an options window where you can switch back and forth between the small molecule and the protein modes of the program. Click OK, and that should put you in PX mode. Now I'll just give you 2 quick tips. If you're processing PX data, it's helpful to install CCP4 on the computer where you're doing your processing. That will give you access to some features in CCP4 and give you this CCP4 button here on the left of the interface. The other thing I would recommend, and my second tip, is that you update to the latest version of CrysAlisᴾጴ. You'll see at the top of the screen here, I'm using version 40.75a. And if you need to update your version, you just go to the bottom of the interface, find your help menu, which is this question mark, go to the menu next to it, and select check for new version. CrysAlisᴾጴ will then hunt out on the internet, show you whether you're using the latest version, allow you to download the newest version and install it. Next, let's talk about the layout of the software. You see in the middle, the biggest area, the main area, is devoted to looking at your diffraction images, and the controls for manipulating the images reside on the bottom toolbar. On the left-hand side, we have a series of buttons or power functions, and we'll go over a few of these during the webinar today. On the right-hand side, we have a series of executive tabs that give you summary information about whichever part of the experiment you're in right now. The first thing I like to do with my data set is a visual check. So one thing you might like to do is make sure the images are viewed at the proper size that you like to look at them. So we've got a plus button on the bottom, which will zoom in, a minus button will zoom out. So put it exactly at the zoom level you'd like to look at. You might also like to change the contrast and the coloring of the images. So the little starburst button on the bottom will allow you, if you click on it, to go through the different levels for the contrast. If you use the little menu next to it, you can pick the contrast level out of a list. Likewise, the paintbrush button will allow you to go through the different colorizations that CrysAlisᴾère has for the diffraction data, mostly to help you look at your high resolution weak spots. You can use the little menu next to it to pick the colorization you like. I'm going to choose X-ray film. You might also want to turn on the information for the displayed image. So for that, what you're going to do is click on this circle K, and you will see the image name and the goniometer angles where this image was recorded. You can click on this with a right click and drag, and you can move that label out of your way. The first thing that I like to do after I have my view all set up is I like to play the diffraction data set with this play button on the bottom. And that will quickly play through the data set. I know that on Zoom, you might see this as a little choppy or only see a few frames of it. But trust me that on your own computer, you'll see all the frames. And what this will allow you to do is let your eyes see some pathologies that you might find in a data set, like ice, multiple lattices, the pin goes in the beam. And so you just want to have an idea of whether you are dealing with some other problems besides what your sample looks like by itself. The next thing we want to go over is the beam stop mask. So you can see on these images, I have a shadow for the beam stop arm and the cup. And so if I want to see what the mask looks like for that, I'm going to click on the command window. The command shell opens, and it may open above what I need to see, which is the shadow. So I'm going to left click the top of the menu, drag it out of my way so I can see this shadow here. And then I'm going to click on the options button to get to all the program options. Again, if it's in your way of seeing what you want to see, left click the top, drag it out of your way. Then I want to click on the tab that says beam stop. And I want to click on put beam stop overlay on. And here you will see the mask for that beam stop. And it's obviously too large. So the controls are right here on this panel. The first thing I'll do is click on diameter, and I will change the cup diameter from 2, which is the current value, to 1.5. And that makes the cup smaller. And then I will change the holder diameter for the arm. Click on holder diameter. Current value is 3. I will make it 1. Click OK. And now that is smaller as well. There may also be an angle in your holder arm. So there's an angle button here. I can click on it and then enter an angle. So just by way of example, if I put in a value of 10 and click OK, you can see which way the mask is moving. That's not the correct direction. So I click again. Maybe it's more like 359.5. Okay. And that's about where I want to be for the beam stop shadow mask. Once you've set these parameters, you're done. But since I'm here anyway, I'm going to give you my tip number 3, and that is to click on the peak table tab. And the peak table tab will show you what the number of peak threshold is for doing peak hunting and indexing, essentially. So what I like to do is edit both of these numbers here. I'm going to add a 0 and make it 1,000,000 peaks. And so by making both of these numbers 1,000,000 peaks, when I do peak hunting, I'll be certain to look for peaks on all of the frames of my data set, and that when I do indexing, I'm indexing on the whole data set. Once you've made any changes here in the options, what you want to do is click on Save to PAR file on Exit and click OK. It'll warn you that you're updating the instrument model. You just click Yes. You click Close on the command shell, and now we're done with this part. So we're going to move on to indexing. So to do the indexing, what you want to do is click on the top left power button. The top left power button is the lattice wizard. The picture that you see on the button is a magic wand over a unit cell. So if we click on that, the lattice wizard opens. On the right-hand side, we have all the buttons we would typically need to do indexing, like a peak search, unit cell finding, refine instrument model, and looking at the different types of lattices available. So the first thing we're going to do is click on peak search. If I click on the big button, it's going to do an automatic function. If I click on the little menu next to it with the caret symbol, I get a drop-down list and I can do something customizable. So I'm going to do the peak search with user settings. And in the peak search with user settings menu, I can choose to truncate the data set and hunt on less frames in the whole data set. By default, we're going to look on the whole data set. Why I really entered this menu was to change the type of peak hunting from an automatic threshold and background detection to a smart peak search. The smart peak search was optimized for protein data sets and takes varying background on the images into account when it's hunting for peaks. So click OK, and the peak search will run. When it's finished, the window will display how many peaks were found right here. So we've got about 42,000 peaks were found. And right now, 0 of them are fit, 0% are fit because we haven't auto-indexed. So there's the next step. We're going to go to unit cell finding and click the button. And we will index the cell. So you can see on the top line, we have the current cell, A, B, C, alpha, beta, gamma, and a volume. Underneath that, we have a constrained cell where A equals B and all angles are 90. And underneath that, with the selected cell, you can see that CrysAlisᴾṕRO has chosen a tetragonal primitive lattice for this sample, which happens to be correct for lysozyme. Further down, you can see this percentage of indexation. So we've got about 91% of the spots indexed, which is very good. The next thing we want to do is see if we can improve this by refining the instrument model. We click on Refine Instrument Model, and that would run a refinement. What I like to do is use the little menu next to it, Refine Instrument Model with User Settings. And all I want to do here is turn off the automatic selection of parameters. And I just like to make sure that the wobble vectors 1, 2, and 3 are all turned on for this refinement. It refines, and we went up from the low 90% to about 96.3% indexed. I can keep pressing the refine instrument model to see if I've converged, and it looks like I have. That's the most that we're indexing, 96.37%. If you need to inspect the Bravais lattice table at this point, you can click on the lattice transformation button. This will show you the lattice types starting at the bottom from triclinic and going all the way up to the highest symmetry lattice that would still fit this sample type. And the distortion index is reported here on the right-hand side, last column. So you're only going to see distortion indices that are low. Any that are high are just not even going to be shown. So the highest symmetry thing that still fits for the sample is tetragonal primitive. However, if you knew for your particular sample that it's not really tetragonal, that you have an orthorhombic sample, you could pick that out of this list, hit OK, and then you could refine that. So we'll keep ourselves here at tetragonal, click OK. The index percentage drop back down. I'm just going to re-refine it to convergence by clicking on Refine Instrument Model one more time. And there we are. We're back to where we were. So we've got a really good indexed sample according to the index percentage. Now, if you'd like to visualize the results of indexing, I recommend that what you do is you click on the Ewald Explorer. So that's this button right here. We're going to click on Ewald Explorer, and this is a reciprocal space viewer. By default, it's going to open up and take up the whole screen. So let me just resize it so we can see our labels here on the left. So let's go to Ewald Explorer. And so the basic controls for the reciprocal space viewer are you hold your left mouse button down and then you drag around your mouse and you can rotate the reciprocal space view. So you see all the spots that were collected during the peak hunting in reciprocal space, and in the center what you see is a grid for the unit cell that was found, okay? If we right click and hold and we go up, we zoom in, we go down, we zoom out. Now the most useful way to view this is to view it down one of the axes. So you can click on A star, B star, or C star, and you can see how well these spots line up with the vertices on this unit cell. On the right-hand side of the interface, what you can see is a series of the projections and how well they line up. So what's considered to be on a lattice point has to fall within a tolerance defined by the red, green, and blue boxes. And you can see we have very sharp peaks falling on these lattice points. We don't have a lot of stuff going on in between, which is good. And so this viewer is really good for you to see how well the indexing works, and it's really good to see if you have other pathologies in your data set, like some ice or another crystal or what have you. So once you have judged the sample, the indexing, by looking at the lattice viewer, you just want to click the X on the top right, and that will exit out. And you click close on the lattice wizard, and now we have indexed our sample. We're ready to move on to data reduction. And so everything is going to start with the start and stop button on the top right of the interface. We click start stop and we get a menu. And so we're going to choose data reduction with options. And that's going to bring us into a series of menus. We only have to do one or two things here for this particular data set. Many of the options are you're just going to click next and go to the next menu. So the first menu is orientation matrix for data reduction. We have nothing to do here, so we're going to click next. The next menu is the experiment run list for data reduction. So this menu allows you to trim the data set if you knew there were problems, like you knew that the last 50 frames of the last scan were bad, you could truncate that particular scan right here. In this case, we're using everything, so there's nothing to do. We click next. The next menu is basic algorithm parameters. And typically what I would do here is click on edit special parameters. And I want to make sure that this use resolution limits checkbox is actually unchecked. And when it's unchecked, I will be sure that I will integrate all the data on the detector even into the corners. And then I will click OK. Then I will click on next. The next menu is for background evaluation. The defaults for background evaluation for PX sample are already set fine, so there's nothing to do here. We can click on next. Outlier rejection is the next menu. Again, the defaults are fine to use outlier rejection, so we click next. And this is the last menu, the output. So typically when you're running an experiment with CrysAlisᴾère, the data processing is going to proceed automatically, and you're going to get an automatic processing result. So what I like to do if I'm reprocessing it myself is click on change the output name. And this reflection file here listed at the top would be what CrysAlisᴾère had done by itself. I use the same name. I add my initials to it. So I have a different output file for when I process the data myself. Click OK. I'm just going to overwrite this file, click yes. And so that's the way that I do this. So I'll have two different sets of processing. And then when you're all done here, you'd click on the finish button and the software would go through and you would see visually that it's doing the background estimations, the profile fitting, and the integration. But rather than having you wait here for 3 minutes while this runs when I click finish, we'll just run this like a cooking show, and I've done the processing beforehand. So instead of pressing finish, I'm going to cancel this, and we'll just come to the next step in the process, which is looking at the quick summary. So when the data were finished processing, what would happen is the executive summary tab for data reduction would pop up, and you would see some information for what happened during processing. There's a few things that I look at here quickly just to see how things went. First of all, there's 686 frames in the data set. I'd like to see that the frames done is all of the frames were used, which is good. Under 3D profile analysis, I'll look quickly at the average mosaicity in degrees in 3 directions, E1, E2, and E3. Looks pretty good. You can make a note of what's under scaling numerical absorption. These are corrections that CrysAlisᴾểu chose by default, and you can choose to make different choices when you do rescaling. And maybe most importantly here, under results, we have the whole data resolution range to 1.5 angstroms and the highest shell, and we have the redundancy, 8-fold overall. The I over sigma is 3.6 in the highest shell, and the rint, which is the same as the rsim, which is 3.7% for the whole data set. So it looks like it's a pretty good data set. Underneath that, you'll see the space group descriptor. So CrysAlisᴾểu originally chose P41212, and I knew that it was P43212, so I changed that when I rescaled it, but we'll look at that more in a moment. If you want to look then at the full results, you need to click on the results inspector. The third button down on the left has a series of 1s and 0s and an arrow pointing to a piece of paper. This is the results inspector. So I click there, and the inspector launches, and what I'm going to do is resize it. And when it launches, what it does is it brings you to a tab called Data Reduction Output, and we're basically at the end of the log file after scaling. And so we're right at the bottom of the log file next to 2 tables that have statistics versus resolution. The table at the bottom has the anomalous pairs merged, and the table above it is with the anomalous pairs unmerged. Okay, so for the table on the bottom, you can see that we've processed all the way down to 1.5 angstroms. We have a completeness going to 88% overall, but we're only about 34% complete in this high shell, and the redundancy is pretty low. Remember that the strategy for this data set was really to 1.7 angstroms. The I over sigma shows us that we've got a good I over sigma all the way out to 1.5 angstroms. And the rint looks pretty good overall, 3.7%, and it's only 20% in the highest shell. We've also got the CC1/2, the rrim, and the rpim statistics in this table. The table above with the anomalous pairs unmerged, the last column has your anomalous signal to noise versus resolution. In this column, whenever you have values that are above 2, it's a good indicator that you've got an anomalous signal. And as I mentioned, this data set does solve by sulfur SAD phase. Okay, so you might also, besides looking at the information in these tables, like to take a look at a few of the graphs that are generated during scaling. So you can click on the Reduction Graphs tab. The first plot that you see here is the scale factor versus image number. And so the scale factor is here in red versus image number. And you also see simultaneously a blue plot that's showing you the different scans. So this blue line here is basically the divider between scan 1 and scan 2. And this one, the divider between scan 2 and scan 3. And you can see that the scale factor is nice and flat across the whole frame range, which is pretty good. In the drop-down list on the bottom left, it has a source data drop-down list. You can pick other data that you'd like to look at. Maybe you would like to look at the B factor for the data sets. This is B factor versus frame number, which again looks pretty flat for this data set. And another one you may want to look at is the rint per frame, which again looks pretty good for this data set. If you see anything alarming to you or an outlier while you're looking through these plots, you just want to make note of it, and you can use a filter later in rescaling to eliminate it. So for example, if in this rint plot, if I saw one particular frame that had an rint that was, let's say, something outrageous like the number 1, I just keep that in mind, and I could choose to filter it out afterwards. And I'll show you that in rescaling. which is what we're going to do next. So if you want to rescale the data, you have to know that in CrysAlisᴾṕro, rescaling is really called refinalizing, just a different name. So if I click on the bottom left of this interface, I see this button that says Refinalize, which brings me to the refinalizer. There's a few things you'd want to do here. First, you have some options under corrections. You can click on Manual here, and you can see that we have a few options. One would be to change the type of absorption harmonics. So this is spherical harmonics that are being done. Right now it's set to auto. CrysAlisᴾṕro is choosing the even and odd order terms. Like I mentioned before, you can see which numbers for even and odd it chose on the right hand side in the executive tab, or you can choose to set these even and odd order terms yourself. I'll leave it on auto. For the frame scaling, you can choose how many frames are used per scale factor by doing set and choosing something out of the list, or you can let CrysAlisᴾΠRO decide by using auto. The last option here that I'll mention is the detector correction. This is a way for you to grid up the detector into, let's say, a 6x6 area for CrysAlisᴾPRO to do local scaling on the detector. And so for any of these options, I would recommend running scaling several times to see whether or not these options are helping you achieve better statistics. On a good data set like this lysozyme, they're not going to make a huge difference. Under space group, the search for the space group is going to be automatic, and it will prompt you for potential solutions. And so you'll see that in a moment. Under filters and limits, I recommend that you click on manual. And this is where you can enter your high resolution limit and do a cutoff for the data set. Since we saw we had a low completeness going to 1.5, let's just try cutting this at 1.6 angstroms. Here is also where you could add a filter if you saw some problems in the rint plot per frame. You click on filters, you click add. You have to choose the type of filter you want to use. So in this list, I would pick rint frame filter, and I would pick anything that had a value greater than 0.3, let's say, is going to be excluded. Click OK, and I've generated this condition now. I click OK, and you can see the software is reporting I have one active filter. So that's the filter I use most often, is the rint filter. There's another filter in there for excluding certain frames from certain runs, and that's another one that I would use. The last thing that you'd like to do is under output, if this is a PX data processing, you want to click on export options. So CrysAlisᴾPRO is by default going to export a .hkl file that's got your data set. But those of us doing PX structure solution would like to have an MTZ file. So after you've opened export options, what you want to do is click on export MTZ. And what CrysAlisᴾPRO is going to do is export an unmerged MTZ file that you can then use another program to generate a merged MTZ file. In this case, because I have CCP4 installed, we're going to be using CCP4 scaling using Aimless to give us the merged MTZ file. As soon as I turn on export MTZ, I have this CCP4 scaling button on. When I click that, you can see that use MTZ data scaling with CCP4 is on, and I have a project, crystal, and dataset name assigned. Click OK. Click OK again. And now you can see it's reported at the bottom, exported files, MTZ, this would be the unmerged MTZ, and CCP4 scaling is on, and that will run Aimless and generate our merged MTZ file. And then I will click OK, and CrysAlisᴾPRO will begin computing and running the rescaling. And when it gets to the portion about deciding on the space group, I will get prompted. These are the available space groups that would potentially fit the data right now. So I have P41212 and P43212, and it can't tell the difference because it's just a hand change. I happen to know the answer, so I'll select P43212, click OK, let it finish the scaling. As soon as the scaling is finished, you're going to see a message pop up where CrysAlisᴾPRO has run a script to run CCP4. So here it is, pointless started, and then it'll say that pointless is finished and aimless is started. And so when CCP4 jobs are finished, I will regain control of the CrysAlisᴾểu interface, and I can take a look at the statistics. Now the message that pops up really quick there at the end says CCP4 scaling failed, and that is just a bug that we have to fix right now. It actually finished just fine. So if I go back to the data reduction output tab, you can see we're back to those two tables at the end of the CrysAlisᴾểu log file. And indeed, the data were now scaled to 1.6 angstroms as the high resolution limit, where I have 80% completeness in that shell. And the overall completeness now is 97%. So what we're really after here is the results from the CCP4 scaling. So what we're going to do is click OK here to close the scaling from CrysAlisᴾểu. And we're going to come back out to find our output files. We need to go back to our directory tree, which I got to move this little thing out of my way to see my directory tree. Here it is. This is my experiment directory. And the easiest way to find the CrysAlisᴾểu output files is to sort this by the date modified. And the last file to come out here, you see this _mdc.mtz is the unmerged mtz file that CrysAlisᴾểu exported. The file above that says _red.sum. This is the log file from that processing. So now if I want to go to the CCP4 stuff, I would sort this by name, go up to the top, and you can see I have a CCP4 directory. I double click that to enter it. I double click on the project to enter that. And these are all the files generated from the CCP4 jobs, the output files, the plots, and the log files. So I'll just point you to a few files here. First of all, this MTZ file is the unmerged MTZ file was copied over here. The MTZ file at the bottom that has the word scaled 0 appended to it, this is your merged MTZ file that you would use to go on and solve your structure. And you also would like to inspect your log file from aimless, log aimless.txt, which I have over here, and scroll down to the bottom of that log file, and you'll see the results of the statistics versus resolution from aimless. And since you are merging the data with aimless, this table here with these statistics, this is what you want to report in your table 1 for this structure. The last thing I'll do is just, again, point to the fact that there's a significant anomalous signal in this data set to 2 angstroms. So we've gone through and we've processed a typical, easier protein data set. So right now I am finished. I would like to thank you very much for listening. I hope you all stay safe and healthy during this time. And we welcome your questions and also your suggestions for future topics for this webinar series.